Hey everybody, these notes are the introductory notes for Unit 6 of the gases. We will be taking a look at a number of different gas laws this chapter, and we'll start out with the ones that are a review from last year. So here we go. Before we get into the gas laws, we need to talk a little bit about pressure. Pressure is one of the primary gas variables that we're going to be talking about, and a couple of words of note on pressure. First of all, it's worth noting and assume that gases uniformly fill their entire container. If you release a gas in one side of a container, it will spontaneously fill the entire container without any outside influence. Gases fill their container completely. Gases mix completely with other gases too. All gases, whether or not they're polar or nonpolar gases, mix completely, so they are unaffected by differences in polarity. And finally, gases exert a pressure on their surroundings, and the surroundings in this case is whatever container they're being held in. So whether it be a variable volume container or a fixed volume container, gases are exerting a pressure on the surrounding environment at all times. Pressure is defined as force divided by area, and there are many different ways that we can apply pressure. There are many different derived units of pressure. The SI unit for pressure is Newton divided by meter square, and that is represented as 1 Pascal, named after a French scientist who came up with the unit himself. Now, if you're taking a look at what a Pascal really is, it's a Newton divided by a meter squared. So in other words, if you draw a square meter on the ground and place a Newton weight inside that, you would be representing the pressure of roughly 1 Pascal. 1 Newton is equal to less than 1/4 of a pound. So if you're thinking about how much a Pascal really represents in terms of pressure, the answer is not very much. That force of the weight on 1 square meter, which is a fairly large amount, it's roughly 3 feet by 3 feet, is not a lot of pressure. And so instead, scientists tend to use 1,000 times a Pascal or a kilopascal. Another derived unit from the Pascal is a standard atmosphere, which equals the weight of a column of air at sea level. That is equal to roughly 1 meter by 1 meter. So again, if you take a 1 meter by 1 meter patch of land near sea level and you measure the weight of the air over the top of that square meter, that equals roughly 1 standard atmosphere. Now, to set those equal to each other, 1 atmosphere is equal to 101,325 pascals, or 101 kilopascals. If you round this number off to 3 digits, you'll get 101 kilopascals. So 1 standard atmosphere is 1 ATM. Another unit of pressure that we use is an old version of pressure, but it is still one that is used pretty regularly, and that is millimeters of mercury. This comes from the old use of a barometer, where a barometer used to be a dish filled with mercury with a tube of mercury sticking out of the top of it. So inside the tube of mercury, there'd be a rough level, and inside this would be a vacuum, because you fill it up with mercury completely and then you tip it up vertically, and just the weight of the mercury would pull down because of gravity, and it would create this empty vacuum space at the top. The level at which the mercury would sit was equal to 760 millimeters, and that was equal to the atmospheric pressure pushing down on the open disc. It's like the dish was a wide open dish, and the atmosphere would push down on it, and the atmosphere would force the mercury up. Now, under high pressure systems, this level would go up higher. Under low pressure systems, this level will go down lower, but at standard conditions, the level inside the tube was 760 millimeters of mercury, which is where they get that standard millimeters of mercury. To translate that to another unit used in Italy, torr is short for some Italian guy's last name, Torricelli or something like that. But 1 millimeter of mercury, which is kind of a mouthful to say, was kind of shortened down to 1 torr, which is where you get 760 torr. So watch out for all these different pressure units: Pascal, kilopascal, atmosphere, millimeters of mercury, or even torr. Now, you're not going to be tested on this. This was just to give you a little bit of context as to how millimeters of mercury was even used in scientific explanations. Now, I added this slide into the notes, and so I recommend you do so as well. We already talked about one of the gas law variables, pressure. All gases exert a pressure on the container that they are in. Volume is another key variable of gases. Volume represents how much space the gas takes up. Another key variable is temperature. Now it's important to note that temperature is usually measured in degrees Celsius in everyday situations, but for gas laws you need to translate that to Kelvin or absolute temperature. Now what's nice is, if you remember, 1 degree Celsius is equal to 1 Kelvin. It's just that the scales don't start at the same spot. In order to get your degree Celsius to Kelvin, you need to add 273 to your degree Celsius. So that's on your useful list of variables and constants, but I wrote it down just in case you needed it. The last gas law variable that you need to be familiar with is number of moles of gas. Moles of gas is represented by the variable N, and we use that not only in the ideal gas law, but there's going to be some other gas laws that I'm going to introduce to you that will relate moles of gas to pressure and volume. So pay close attention. One of the first gas laws, if you remember, is Boyle's law. In Boyle's law, we are going to be taking a look at the effects of pressure and volume on a sample of gas, whereas temperature and the number of moles of the gas are held constant. In all these gas laws, we're going to talk about the 4 variables. 2 are going to be messed around with, and 2 are going to be held constant. In this case, temperature, number of moles. So, if you remember from last year, pressure and volume are inversely related, which means one goes up and the other goes down. And this makes sense because if you're holding a balloon in your hands and you squeeze it from the outside, the volume is going to decrease. So as the pressure increases by the squeezing of the balloon, the volume decreases. This is also represented in a variable volume piston. If you look at it, you have this piston that can compress the gas, and as the plunger goes down, the pressure inside increases and the volume decreases. So as the volume goes down, pressure goes up. Basically, you're taking the same amount of gas and decreasing the amount of space that it has to roam around in, and thus the pressure will increase because you'll have the same number of particles occupying a smaller volume, and so the pressure increases. Those particles bump into each other and bump into the wall, increasing the pressure or the force on that area. Now P times V for any sample of gas is equal to constant K. And if you change the pressure, the volume changes proportionally. And if you set those two equal to each other, P1 times V1 equals P2 times V2. Now what's happening with the gas molecules in this law, and we explained it with the variable volume container here, but the gas molecules are being compressed, and so their pressure increases because they're colliding with each other and the walls, essentially exerting more force on a smaller area. Remember, our definition of pressure is force divided by area, and if you make the area smaller, if you make the denominator a smaller number, the value goes up. So by making the area smaller, the volume smaller, you increase the pressure. Here's a graphical representation of Boyle's law, and if you look at the x-axis, the y-axis, you got pressure in kilopascals. It could be pressure in atmospheres, but it really doesn't matter. And as the pressure decreases, the volume increases. And notice it's not linear. It's kind of an exponential decay. Now at extreme pressures and extreme volume changes become less predictable. And so this is best represented in pressures at or above 1 atmosphere, or normal Earth-like standard conditions. We'll talk about the situation and how gases deviate from the standard. It's one of the important learning targets at the end of this chapter, and we'll talk about that. We'll talk about extreme hot, extreme cold, extreme pressure situations. So stick tight. But for now, all you need to know is Boyle's law best holds at or above 1 atmosphere of pressure. Next up is Charles' law. Charles' law takes a look at the relationship between volume and temperature, of course in kelvins, and how they're directly related. Keep in mind the other 2 variables, pressure and number of moles, are being held constant. We talked about this already, but when you're converting from Kelvin to degrees Celsius or degrees Celsius to Kelvin, you add 273. Down here is the gas law. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. And if you're going to have a problem mathematically that deals with Charles' law, you'll be given 3 out of these 4 variables and you'll be asked to solve for the 4th variable. That goes for all these gas laws. You'll be given all the variables except 1, or the means to find all the variables except 1, and be asked to find the missing variable. And there's some practice problems in the bookwork, and I strongly recommend you check those out. Here's what Charles' law looks like graphically. As you can see, it's a linear linear graph. Now, along the x-axis, we actually have degrees Celsius, which is why this can go below 0 or past the vertical axis. But it does reach 0, meaning 0 volume at negative 273, which is absolute 0. But as the temperature increases, the gas particles begin to move faster with more energy, and as long as you hold the pressure constant, the volume, the variable volume, as you can see, this piston can scoot up and down. So here at a low temperature, we have a low volume because the particles don't have a lot of energy. They're at a low temperature. But as you boost the energy and increase the temperature, they begin to move around with more vigor and more meaning, and they can basically push the variable volume container up, increasing the volume, keeping the pressure constant inside. Gay-Lussac's law takes a look at pressure and temperature again in kelvins, keeping volume and number of moles constant. Looks a lot like Charles' law, and is indeed a lot like Charles' law. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. Again, you'll be given 3 out of the 4 variables, and you ask to be solved the other missing variable. There's not going to be a picture or graphical representation of Gay-Lussac's law, but since it's so similar to Charles' law, you can expect it to be a direct linear relationship. It would look something like this. If this was temperature in kelvins at absolute 0, you'd have 0 pressure, and as you increase temperature, you increase pressure proportionally. Now, if you combine all these gas laws together, you get what is known as the combined gas law. Real original name, right? It combines Boyle's, Charles, and Gay-Lussac's law. So if you're looking at just pressure and volume, that's Boyle's law, or pressure and temperature, that's Gay-Lussac's law, or volume and temperature, that's Charles' law. But all three of them are in this delicate little three-way dance. And if you've got all these variables set equal to each other, and you're given 5 out of the 6 variables, you should be able to solve for the missing variable. So if you got pressure 1, volume 1, and temperature 1, set that equal to pressure 2, volume 2, temperature 2. You've got the combined gas law. I wouldn't spend my time too much trying to memorize the individual gas laws because they're easy to mix up. You do need to know the individual gas laws and the variables that each one are testing, or in other words, the variable that each one is holding constant. But when it comes to doing calculations, I'd stick to just the combined gas law. And if something is being held constant, you just take it out. So like, for example, if temperature is being held constant, these would be the same number, so they essentially cancel out of the math. Or if your volumes are being held constant, they'd cancel out of the math. Or the pressures are being held constant, they'd cancel out of the math. Combined gas law assumes that the number of moles is continuing to be held constant. Now you might be asking yourself, why the hell am I talking about the number of moles if it's always going to be held constant? Well, you're in luck. The next gas law talks about how number of moles is related to volume in what is known as Avogadro's law. Avogadro's law, yes, that Avogadro, the same guy who gave you the Avogadro's constant of 6.02 times 10 to the negative 23rd, was the scientist who was doing his experiments with gases. In fact, he came up with his constant from experiments involved with gases. His law and his observation showed that the volume and number of moles are directly related to each other, no matter what the identity of the gas. So it doesn't matter if you're talking about a sample of hydrogen or a sample of carbon dioxide. The number of moles and the volume of that gas are related in this way. The more moles you have, the more volume you have. That seems to make sense. Assuming you keep the temperature and pressure constant, let's say you take a volume of gas and you have a number of moles of gas that are set, and then you somehow are able to introduce more moles of the gas, so you increase the number of moles of gas. It makes sense that since pressure and temperature are being held constant, the volume is going to expand to make room for that extra gas, and so they are directly related. The number of moles of gas divided by the volume of gas is equal to the moles of gas at a new number divided by the volume of gas. Now, the reason the identity of the gas doesn't matter is because the actual volume of the gas particles themselves is so small in comparison to the total volume of the gas that they're considered to be negligible. So it doesn't matter if you have a very massive gas like sulfur hexafluoride or a very light gas like helium. The particles themselves are so small compared to the total volume of the sample of gas that the identity doesn't matter. And that's why you can assume that this law applies to all gases no matter what. And this is the gas law that I'm going to leave you with in this video. That takes care of these introductory notes. Thanks for listening.